Hello everyone, I am Aishwarya. I am doing my internship program at Sparks Foundation. Today we are dealing with my second internship task. In this task, from an iris data set, we predict the optimum number of clusters and represent it visually. For that, we have most famous iris data set. Let me give you a brief introduction of the iris data set. The dataset contains three classes with 50 instances each. 150 instances in total, where each class refers to a type of iris plants. There are three classes such as setosa, versicolor, and virginica. Alright. For predicting optimum number of clusters, I use k-mean clustering. K-mean clustering is an unsupervised machine learning technique. Now, let's get started with our task. Firstly, we need to import the necessary libraries for the task, that is NumPy, Pandas, Matplotlib. The most important library here is sklearn. I import dataset module to load the data. Using load iris command, I load the data and then convert the data into data frame format. And using head command, display top 5 rows of the dataset. So, finding the optimum number of the cluster is an important part of this algorithm. For that, a common used model for finding optimum k value is the elbow method. We first need to slice the important feature of the data. With this code, I slice the data. When I am doing this task, I forgot the dot values function of an array. Then I got problem to display the cluster visually. So that's why use of the dot value is necessary. Alright. Now we are using the elbow method to find the optimum k value. In elbow method, we are actually varying the number of clusters from 1 to 10. For each value of k, we are calculating WCSS, that is within cluster sum of square. Within cluster sum of square is the sum of squared distance between each point and the centroid in a cluster. When we plot the within cluster sum of square with the k value, the plots look like an elbow. Firstly, from sklearn clusters, import k-means and then create empty list of object WCSS. Then create a loop for I in range 1 to 11, that is k varies 1 to 10. Then use k-means and of course we need to specify n clusters. In this loop we specify n clusters is equal to I, int is equal to k-mean plus plus, maximum iteration is equal to 300 and number of int is equal to 10, random state is equal to 42. Maximum iteration and n int is default 300 and 10 respectively. You can change as required and then I feed the k-mean to the sliced data and append the k-means dot inertia to WCSS object. Inertia means how well a data set was clustered by the k-means. It is calculated by measuring the distance between each data point and its centroid, squaring this distance and summing these squares across one cluster. Now let's plot the result on the line graph and observe the elbow. From this code we can plot the graph. We can see that the elbow on the graph where the inertia becomes more linear is at k is equal to 3. We can then fit our k-mean algorithm one more time and the plot different clusters. Now this time we can put n cluster equal to 3 and using fit predictor we predict the cluster to the data. So now it's time to visualize the clusters. From this code I plot the scatter plot. In this plot, blue plots represent the Setosa class, red points represent the versicolor class, yellow points represent Virginica, and black points represent the three centroid points. Let's evaluate the performance of our cluster. For that, I use silhouette score method. Silhouette score is used to evaluate the quality of a cluster created using clustering algorithms such as k-means in terms of how well samples are clustered with other samples that are similar to each other. To calculate silhouette cluster, I import silhouette score from the sklearn matrix and using silhouette score function and using the equilibrium distance measure, I calculate the score and print. For 3 clusters, silhouette square is and assign the score. The silhouette score for the cluster is 0.55. As we know, silhouette square vary -1 to 1. And when score is 1, that means the clusters are very dense and nicely separated. So we can say that our clusters are also nicely separated. From this, I am able to complete my second task. If you have any comment, any query, and any questions, let me